Good afternoon to one and all. Myself, Dr. M. Haripriya, working as a principal, FSC, TTWREIS, Janagam. First and foremost, I would like to thank our beloved Secretary Sir for giving me this wonderful opportunity to take the class as real analysis part. So, in the real analysis part, today I want to discuss about the continuous functions. So, before going to the continuous functions, first of all, let me discuss what is the main part or main concept of real analysis. So, coming to the real analysis, so in the mathematics, what do you mean by analysis? Analysis means it is a study or a development or the subject which deals with the real coordinate system. So, actually whenever this real analysis focuses on analytical properties, and it is always takes a particular change which occurs in a particular space. If that particular space, if you are taking a continuous change in a particular space. So, what do you mean by this particular space? It may be a real coordinate system, or it may be a complex plane, or it may be a arbitrary vector space. So, depending upon this particular space, whatever the change occurs continuously, this can be treated as an analysis part. Now, in our topic, we are dealing with the real coordinate system as a study and the development on this real coordinate system. That is why the concept is named as a real analysis. Now, in this part, the analysis always focuses on the analytical properties, such as, if you are taking like this, these are the analytical properties. One is limits, second one is continuity, and third one is differentiation, and fourth one is integration. Like this, if we continue, convergence, and here measurable. So, these are the some of the analytical properties on which the functions can be, the real analysis focuses on this. Now, we are going to discuss the second topic, real analysis. So, what do you second topic here is the continuity part. Whatever the how to define the continuous function, what are the main properties of continuous function, and what are the role models of this, what are the properties of this continuous function and consequences of continuous function. Now, before going to this continuous functions, first of all, let me define the limit concept. So, limit concept is limit of a function. So, if you are taking a limit of a function here, let f maps S to R, where S is a subset of R, in such a way that here we are taking, let A be a point in S and L is a real number. Now, we are taking A is a point in the domain and L is a real number, such that the function f of x, whenever it approaches to L as x approaches to A. Symbolically, this can be represented by limit x tends to A, f of x equal to L, and here as x tends to A, we does not bother that the function is defined at the point A or not. So, how we can take this as a classical definition here means, let me come to a classical definition, and this definition you can suppose it as an analytical definition. So, coming to this analytical definition, limit x tends to A, f of x equal to L whenever x approaches to A. Now, coming to here, classical definition of limit of a function. So, classical definition if you are taking, if for every epsilon greater than 0, there exists a delta greater than 0 such that the modulus of f of x minus L less than epsilon whenever 0 less than x minus a less than delta. Here this is the main concepts we can go through it. This type of neighborhood is called as a deleted neighborhood. What do you mean by a deleted neighborhood of a point? If you are taking here A is a point on the real line, and we can define for any point, we can define infinite number of neighborhoods. So, we are taking here it is less than delta, this is said to be a delta neighborhood, which we can define it as A minus delta and A plus delta. In this delta neighborhood here, if you are taking a semi open interval and here open semi open closed interval, that means here we are using it as A minus delta A union A comma A plus delta. So, if you observe, it is a closed A minus delta and open A, and here it is open A and A plus delta is closed. That means depending upon this union of all these intervals, simply we can write it as closed interval of A minus delta plus A plus delta minus A is deleted. So, the neighborhood of a point A, which is said to be a deleted neighborhood, means the A point A itself is deleted. This is called as a limit concept, and we are defining a limit of a function in both analytical and classical definition. Now, let we go to the continuous form. So, before going to the continuous form, here we can go through some basic definitions. Already quite familiar about these basic definitions. So, here basic definitions. So, coming to the basic definitions, this is a basic definition of a function. Already it is quite familiar to all of you that the function is defined between any two non-empty sets, where the first set is said to be a domain and the second set is said to be a codomain. So, we are taking an example here, domain of A, ABCD, and the domain and the codomain is DEF, and the mapping or the transformation is indicated by the function F. So, the set of all elements of A is called as a domain, and the set of all the images of these particular elements which are existing in A is said to be an images, which is denoted by F of A. This is an example. Here you can observe one more notation, range. So, here we are defining a function between the set A and B, and the function is defined in between A and B, and the function is taken as 2x plus 1, and the domain is taken as 1, 2, 3, 4 in the first set, and the second set, which is defined as a codomain, it is taken as 1 to 10. Now, here the range part, whatever the 1, 2, 3, 4 elements are assigned to 3, 5, 7, 9. The set of elements which are taking as the images of the each and every element of A is said to be a range. So, if by taking the differences between the codomain and the range, what is the main difference here you can take here is, codomain is the total set of B, whereas the range takes only the set image set of all elements. So, whenever this codomain is equal to range is equal to codomain, then you can say it is called as an onto function. If the range is subset to an codomain, then you can say it as a into function. Now, coming to some simple definitions of different types of functions. If you are taking here f maps A to B, here if A is a real valued function, that means A is a real subset of R, then it is said to be an real variable function. If B is the subset of R, then it is said to be real valued function. If both A and B are the subsets of R, then such type of function is said to be a real function. These are the different kinds of functions which you can discuss. And if you are taking a example of this function, real valued function in our daily life, the both cost and the revenue are the two terms in which the input is exactly equal to one output. So here revenue and the company, if the products, number of products will be produced, and here the revenue are the total number of products sold. So if we observe, the outputs will be the real values. That's why these both the terms can be considered as a real valued functions. So these are some of the examples if you are taking here, and they are defined in a particular domain. As the first example, if you take f of x equal to 1 by x square, the domain is r minus 0. So here it is a deleted neighborhood of 0, and if you are taking it as a f of x second function 1 by 2x minus 1, the domain is r minus half. Similarly, the third and fourth examples are carried out for the real valued functions. Now coming to our main topic, meaning of continuous functions. So literally what is the word means that continuous. Continuous is nothing but a mathematical term. It's not a tool or a process or an algorithm or a theorem. It just refers to a behavior of the function. It is an idea about the niceness. The property of continuity is exhibited by various aspects of nature. That means continuity applications can be observed here in our daily life by using some type of examples. You can go through these examples. The water flow in the river is continuous. The flow of time in human life is continuous. Traffic on road is continuous. Flow of blood in human body is continuous. Now what is the role of continuous function? Why these continuous function we want to propose in the real analysis part? The continuous function is nothing but it is a sufficient data which can be defined for the integration, and it is the necessary condition for the differentiation. As we know that the general statement which is very familiar to us is every differentiable function is said to be a continuous function. That means already the function is satisfying the continuity property, then you can go through the differentiation. Now continuity of a function, let me discuss the continuity of a function in two ways. One is at a point, at a given point, and other one is over an interval. Now let me discuss the two definitions. So we are coming to the main part of this topic, definition of a continuous function. So first let me take continuity at a point. So coming to the literal meaning of continuity, we can draw a graph. For example, we are taking a graph here, just drawing a graph without lifting the pen or pencil throughout, isn't it? So if you observe, the graph is drawn from one point, some point A, and to a point B without lifting the pen. So this flow of the curve is said to be a continuous. Now if you want to define this function continuous at a point, so let us take, there exists a point on the real line, and this can be an x-axis and this can be y-axis, which we are treating it as a y equal to f of x. Now if you are taking a point on the x-axis, it means that the corresponding value for this x-axis at the point A, the function to be defined as f of A. So if you are defining a point on x-axis at a particular point, and let us take some interval here, if you want, some C and D. We are not bothering about the other point, just we are defining the function, we are defining the continuous of a function at a point A. So this definition, wherever the real variable x approaches to this a, the function f of x approaches to f of a. That means here symbolically you can show that limit x tends to a, f of x equal to f of a. So, generally the statement of this continuous function, the limit of the function is equal to the functional value of the function at that particular point, then you can say it is said to be continuous. Now, how this is possible whenever we are defining a function at a particular point? That means to define the continuity of a function at a particular point, we have to take three conditions. So, what are the three conditions here you can observe is, first of all, a should be in the domain. We are taking a function, let us define the function f maps S to R. If f maps S to R, what is the first condition to be satisfied? Whatever the point A we are choosing, that should be lies in the domain itself, and here f of a to be defined. Whatever the function we are treating from S to R, at the particular point A, the function is defined. And the second condition is the limit of the function exists at this particular point. The limit of the function exists at this particular point. Whenever we are saying that the limit of the function exists at a particular point, we have to discuss in two cases. Why? Here if you observe on the real line, the point lies on the real line, but it may goes from the left or it may comes to the right. That means x may approaches to the left side of a, or x may approaches to the right side of a. That is why whenever we are defining a limit of the function at a particular point, we have to discuss in two-sided, both the sides here the limit should be existed. That limit is called as left hand limit and right hand limit. So, left hand limit means limit x tends to a minus f of x, and right hand limit is limit x tends to a plus f of x. So, we are saying the second condition is limit x tends to a f of x. Wherever this limit x tends to a f of x exists, we have to verify that limit x tends to a minus f of x exists and limit x tends to a plus f of x exists. Not only if they are existed, what is the condition to be satisfied? So, here the condition to be satisfied is both the left hand limit and the right hand limit to be equal, and that value should be equal to the functional value limit x tends to a f of x equal to f of a. This is the third condition which you can observe. So, whenever any function which maps from a domain to R, such that if that function satisfies these three conditions at a particular point, then you can say that the function is said to be continuous at that point. This is a definition of continuity of a function at a particular point. Now, coming to the second definition, continuity of a function on an interval or over an interval. So, if you are taking an interval, here the case you have to discuss what is the interval to be. It may be a closed interval or it may be a open interval. Whenever we are saying it as an on an interval, we are choosing a point as interior point. That means we have to discuss the function continuity at interior point, and second one is at the end points. If we can define the function continuity at this interior point and at both the end points, then such type of condition is satisfied, then you can say that the continuity of a function can be defined over an interval. So, how it is possible? Let us take C belongs to an interval a comma b, that means C is an interior point, and we know that previous case we have discussed the continuity of a function at a particular point. Then you can take limit x tends to C, f of x to be equal to f of C. So like this, if you are taking an interval a to b and all the interior points, you can define that the function is continuous. Same definition is applicable for the conditions. Now if you are going to the end points, how to define to the end points? If you observe here, to discuss are the x approaches to the right hand side of A and x approaches to any point in the interior from the left hand of B. That means whenever we are defining the function, continuity of a function at an end points, you can take the definition like this. Limit x tends to a plus f of x to be equal to some f of a, and limit x tends to b minus f of x equal to f of b. If we are taking left end point, we are defining the right continuity. If we are taking right end point, we are defining the left end continuity. That is the careful thing here you have to observe whenever we are defining the continuity of a function over the interval. So if these are the defined and they existed, and for all the interior points the function is continuous, then you can say that the function is said to be continuity over an interval. This is about the two types of definitions. Now whenever you want to say that the continuity of a function over the domain, you are taking a certain domain D and we are defining the function as D to R. We are taking a domain D and we want to define the function f maps D to R. So whenever you are taking certain points in this domain, if at each and every point the function is said to be continuous throughout the domain, then you can say that the function is continuous on the domain itself. So like this you can discuss the continuity of a function at a point, over the interval, and also the domain. This domain consequences gives the uniform continuity of a function. So this is about the definition. And coming to the necessary and sufficient condition for the function to be continuous. So if you are taking the function here f maps S to R be a function, already we discussed in the limit point. Now we are going to discuss the same condition, but it is said to be a necessary and sufficient condition for the function to be continuous. So we are taking f maps S to R and f is said to be continuous if and only if. Where it is continuous at a particular point A, then for every epsilon greater than 0 there exists a delta greater than 0 such that modulus of f of x minus f of a less than epsilon whenever modulus of x minus a less than delta. What's the difference here? You can observe whenever we are taking a limit and the continuity. Same, all the properties are satisfied, but if we observe, instead of L here we are taking the functional value and here we are taking total neighborhood of the point A, whereas the limit of a function we are defining in the deleted neighborhood of a function. That is the main thing. Now coming to the algebra of continuous functions. So let us take f and g are two continuous functions at a point A. We are defining that f and g are two continuous functions at a point A. Then what the conditions are satisfied? There are certain conditions are satisfied by both f and g by taking algebraic properties. First property is f plus g is continuous at the point A. If f and g is continuous, sum of two functions is also continuous. Coming to the second, difference of two continuous, product of two continuous, quotient of two continuous functions are always continuous at that particular point. And coming to the next property, it is said to be a constant here if we are taking, that is a constant multiplication as k into f, where k may be any real number. And the next property is the modulus of the function is also continuous. Now at the last we can observe it is a composition of two functions g circle f, that whenever f and g are continuous functions, following properties are satisfied. Now coming to the main facts of the functions. What are the facts of the functions? That means simply we cannot say that how it is possible. So whenever if you are taking it as a statement, here we can observe. We are saying in the facts that all the polynomial functions means if you are taking some example x square plus 4, or you can take x cube, or you can take some x power n, like this. The polynomial functions are always continuous. And the second thing is exponential functions also you can take it as continuous, and rational functions already we discussed. If f and g are continuous function, the quotient of two functions is also a continuous function. Now coming to the same thing here, the trigonometric functions. Already we know that sin x and cos x are always continuous functions on closed interval -1, 1, whereas cosec, tan, secant and other functions are always continuous functions. Similarly, mod f is taken as a continuous function, and logarithmic functions. These are the facts of the continuous functions. Now coming to the working method. So if you observe the working method, if a function is continuous at a point, then there is no break at all. Already when we observed here, drawing a graph and taking a point a at this a comma f of a, we can observe that the point starts and it ends with to the other point. Now coming to the second point here, if a function f is continuous on the interval, then the graph y equal to f of x is unbroken. When it is unbroken, from the point a comma f of a to the point b comma f of b. The last one is, if the graph y equal to f of x has a break at a point a, then the function is not continuous. Let us see how it is possible. It's a simple notation. I don't want to discuss total depth definitions of discontinuity, just let me recall. So if we observe here, I drawn a sketched totally 4 graphs. Let me discuss what's the difference between these graphs. If we observe here, let me come from the last onwards. If we observe here, the continuity of a graph takes from the first point to the end point. The thing is, I didn't lift any pen or pencil here, and the smooth flowing of the graph is continued from the first point to the end point. That's why this is said to be continuous. Now coming to this graph, if we observe, by drawing a graph here, they make it as a whole, and here it continues the next. So here if we observe this particular point, some a if you are taking, at this particular point the function is not continuous. Actually the function is defined at this point, but the flow of the graph is taken by using a hole. So whenever we are drawing a graph with a hole or a gap, then that type of function is said to be discontinuous. So if you are taking that type of discontinuity, since discontinuity is defined only at a particular point, this point, that's why this discontinuity is said to be removable or point discontinuity. That means if you redefine the function again, then this point can be eliminated. That's why this type of discontinuity is said to be removable or point discontinuity. Coming to the next graph here, if you observe, the graph is continued and suddenly it jumps from this point to this point and it continues. So, if you observe, there exists a gap between the graph, that is why the function is not continuous here. Then what type of discontinuity you can discuss? As the flow of the graph is jumped from one point to another point, then this can be said to be a jump discontinuity. Now, coming to this, there is no flowing and it does not have any particular limit. It continuously flows from the x axis to the y axis. In the same way, if you observe on the positive side, it also same satisfies. So, the thing is, there exists no continuity and there is no end for the graph, and we cannot define the first point and the initial point and the terminal point of the graphs. That is why this function is said to be discontinuous. And what type of discontinuous? You can say it is infinitely discontinuous function, or you can say asymptotic discontinuous function. Now, we just simply by drawing a graph, we have discussed what type of discontinuous acquire in all the type of graphs. Now, coming to the symbolical or the limiting point of the function, how to define these discontinuities. So, if you are taking a continuous of a function, then you can say simply limit x tends to a f of x equal to f of a. This is simple notation of a continuous of a function. But coming to this graph, it is said to be a discontinuous. How it is discontinuous? We can observe on the graph at this particular point the function is not defined. That means the limiting point of this function f of x is not equal to f of a. If this condition satisfies by any discontinuous function, then it is said to be removable discontinuity. If you are coming to the jump discontinuity here, if you observe, you are taking a point and here left side approaches to this point and right side it approaches to this point, but both are not equal at this particular point. That means limit x tends to a minus left hand limit is not equal to limit x tends to a plus f of x. As both the left hand limit and the right hand limit are not equal, then such type of discontinuity is said to be jump discontinuity. Now, if we observe here, both are going to an infinitesimal. That means the limiting of the function from the left hand side is minus infinity and the limiting of the function from the right hand side it takes plus infinity. Both are undefined and they are said to be, they are not equal and it is said to be asymptotic or infinitesimal discontinuities. So, this is about a small r. So, let us check here. The definition is given as f of x equal to mod x. By the classical definition, already we know that we can define epsilon and delta be any two arbitrarily small positive numbers, and we are taking a is any real number in the R. Then if we are defining like this, so let me suppose that the delta neighborhood of the point A at a particular x, if we are taking such that a modulus of x minus a is less than delta, as it is indicated by equation number 2. Now, we want to find out is that the modulus of f of x minus f of a is less than epsilon whenever modulus of x minus a less than delta. It is a simple calculation. By taking here the modulus of f of x minus f of a, we are substituting the value of f of x and f of a values. So, that mod x minus mod a, which is taken from equation 1, and it already we know that the modulus property, that the modulus of mod x minus mod a is always less than or equal to mod x minus a, and already this value is less than delta from equation 2. So, choosing here the delta equal to epsilon such that the modulus of f of x minus f of a is less than epsilon whenever modulus of x minus a less than delta. It's a simple problem. Here we can take directly, we are getting the value by choosing that delta equal to epsilon. Then we can say that the function is continuous. Coming to the second problem, already we discussed in the algebraic properties, every polynomial function is said to be a continuous. I am taking here an example, simple example, x power n. So that the function f of x equal to x power n is continuous at x equal to a. Again here we are taking same process, given function is taken as equation 1 and we are defining a point a in the domain, and here we are taking the function and g of x equal to x. So if we are observing that, as we are choosing that the modulus of x minus a is less than delta, so instead of taking directly x power n here, I am taking it as g of x. This problem is also can be solved by using it as a mathematical induction. F of x equal to x power n, I want to take it as g of x as x. First I want to take n equal to 1. For n equal to 1, let me prove it. As we are choosing that the modulus of x minus a is less than delta, and we want to consider that f of x minus f of a, and here f of x minus f of a can be taken as g of x minus g of a, so that mod x minus a. Already this mod x minus a is less than delta, we can take less than delta. Now let me choose here this delta equal to epsilon. That implies modulus of g of x minus g of a is less than epsilon whenever modulus of x minus a is less than delta. If you want to take it as g square, that means x into x. Already we discussed that the product of two continuous functions is always continuous, then definitely x is continuous, and again x is continuous, the x square function is also continuous. If we continue like this n times, if the product is taken for n times, then you can say that the function is also continuous. That means x into x into x, x power n is said to be a continuous at the same particular point. Now let me come to the next problem, that is f of x equal to, it is a step function which is given as x sine of 1 by x whenever x is not equal to 0. Whenever x equal to 0, we can take it as a 0 itself. Now how to define this function? Again we are taking the same, the given function as equation number 1, and let me discuss in two ways, in two cases. As the point a equal to 0 be a point in the domain, then what happens whenever a equal to 0? Why? Because here the function is defined as x sine 1 by x, and x is not equal to 0 and it is 0, x equal to 0. Now we want to discuss the continuity of a function at this point x equal to 0. So let us take a is any point such that a is taken as 0, then f of a becomes f of 0 which is equal to 0. Now let us choose in the same way x minus a, which is nothing but x minus 0, which is equal to mod x less than delta. Now we want to prove it as that the function is said to be continuous. So that's why we are taking f of x minus f of a, where we want to prove that the function is continuous. It should be continuous at a point x equal to 0. That's why we are taking here modulus of f of x minus f of 0, which is taken as f of x as x sine 1 by x, and this is f of 0 is 0. Now here if you observe, this is said to be mod x sine 1 by x, and here we can take, already we know that the sine function is always bounded in between minus 1 and plus 1, or modulus of sine x is less than or equal to 1. That is why you can use here mod x into 1. Again here already mod x is less than delta, so the total quantity becomes less than delta. So this modulus of f of x minus f of 0 becomes less than delta whenever x mod x less than delta. then you can say that the function is said to be continuous at x equal to 0. So, this is the procedure. Now, coming to the properties of functions, continuous functions. Boundedness of a function at a point and it is in a closed interval. So, boundedness of a function at a point and in a closed interval. So, what do you mean by this? It is also said to be a consequence of continuous functions. Consequences of continuous functions. Consequences of continuous functions means every continuous function is said to be bounded, and it is bounded on any closed interval. This is the first property of continuous function. Now, coming to the second one is preservation of sign. We are taking it as preservation of sign. If the preservation of sign, what do you mean by it? Actually, this is a property which can be used to discuss the bisection of the roots. Whenever we want to find out the location of the roots by using bisection of method, this property is applicable. What do you mean by preservation of a sign? Whenever you are taking any point in a certain interval, so that if f of a is taking as positive sign, then for all the points in the interval, the condition f of x to be greater than 0 for all x belongs to that interval. So, this preserves that the positive sign is satisfied. Similarly, if you are taking it as f of a is negative, then for all the points in that particular interval, if the condition is satisfied as f of x is less than 0 for all x belongs to here, then you can say the negative sign is preserved. Like this, the preservation of sign can be satisfied by using the definition of continuous functions. This is the second property, and the third one is intermediate value theorem. Intermediate value theorem, here you can observe it is used intermediate value property or intermediate value theorem. It is used to find out the minimum and maximum values of the functions at a particular interval. If you are taking a interval a comma b, and we can say that the end points we can define the maximum and minimum here. So, if you are taking these and by observing the values of the functions using the preservation of the sign, this may use to calculate the maximum and minimum values of the function. This is the next property, and the last one is, which is said to be very important, uniform continuity. It is a basic property or the consequences of continuous function. So, here coming to the uniform continuity definition, let me just discuss about the uniform continuity definition. Uniform continuity of a function. Already we discussed that the function is continuous at a particular point. Now, if you want to define that the function is continuous on the domain, we are saying at each and every point that the function is continuous. So, if you observe, whenever we are discussing the continuous of a function, it takes only at a particular point. Other than a, if you want to take, you can take x equal to b, and so that the condition can be taken as x minus a less than delta, and here you can take modulus of x minus b some delta dash. And here this delta, whatever the neighborhood value we are taking, it depends upon the total points on a, b like this, and delta depends upon epsilon also. So, whenever we are defining the continuity of a function, it depends upon where the arbitrary small positive value which is taken as a distance between the 2 points on the real line as modulus of x minus a less than delta like this. If we continue, for different points, the delta depends upon the point and also epsilon in the continuous function. Whereas coming to the uniform continuous, it takes only the value of epsilon. Delta depends upon only the value of epsilon. That is one difference you can observe between the continuity and uniform continuity. And the second difference you can observe, continuity of a function is defined only at a particular point, whereas uniform continuity can be defined throughout the domain or throughout the set. So that's why continuity is always said to be local property and uniform continuity is said to be a global property. So these are the two important differences you can observe between the continuity of a function and the uniform continuity of a function. So here let us take the general definition of a uniform continuity of a function. Let us take, for every epsilon greater than 0, there exists a delta greater than 0, such that as we are defining the continuity of a function only at a particular point, now we are choosing any 2 points in the domain, so that the 2 points maybe belongs to the domain S, such that what we want to take, modulus of f of x minus f of a is less than epsilon whenever modulus of x minus a is less than delta. So here if you can observe, what is the difference between the definition of a continuous and uniform continuous? If you observe here, we are taking the another point in the domain itself, and we are treating the distance function between f of x and f of y as epsilon, and here we are taking it as less than delta. This is said to be uniform continuous. So this is the definition. Here you can go through it. So these are the totally 3 important points. Analog of continuity and uniform continuity already we discussed. Now let me discuss a simple problem depending upon the uniform continuous function. So show that the function f of x equal to x square, we are defining on the interval, closed interval minus 7 comma 7. So in the same way here we are taking modulus, let us take 2 points x and y in the domain itself, and so that the modulus of x minus y less than delta. So how we are choosing the delta? Delta depends upon the epsilon, that's why we want to choose that the delta equal to epsilon by 14. Now you can get a doubt here, why you are taking it as delta equal to epsilon by 14. So if you observe here, at the last case, as modulus of x plus modulus of y, whenever you are taking it as an interval minus 7 comma 7, so both the points are lies between, so that the mod x is less than 7, mod y is less than 7. Depending upon this condition, we are taking that mod x plus mod y is less than 7 plus 7, which is equal to 14. So that's why delta is chosen as epsilon by 14. Now if we come to this point here, f of x minus f of y, x square minus y we are taking, and the product is taken as x minus y into x plus y, so that it is defined as a square minus b square form, and later we are applying the modulus property, and here modulus of x minus a is less than delta, and we are taking mod x plus mod y, and mod of x plus y can be treated as triangular inequality, and this can be taken as mod x plus mod y by triangular inequality, and here both modulus x and y less than 7, and we are taking mod x plus mod y is less than 14. So by taking this, you are getting it as total modulus of f of x minus f of y less than delta into 14. So here this value delta into 14, delta is taken as epsilon by 14, so that it will be reduced to less than epsilon. So totally the function is said to be uniformly continuous on this closed interval. So this is about the part of the uniform continuous, types of discontinuous, and here continuous functions, properties of continuous functions we come across here in this topic. Now I am giving some assignment part which is worked as for important problems for your examination as well as for your competitive exams. So these are the totally problems, you can go through it, totally 8 problems which I post as assignment. Okay, thank you. And once again I want to thank our secretary sir for giving me this opportunity. And also last but not the least, I would like to thank my guru Dr. R. Bharavi Sharma sir, assistant professor of mathematics, who had given full support to be here as in this position. Thank you one and all.